right, the next two problems we are going to work are going to require us to remember some of our trig identities, and in this case particularly, some of our half angle identities. So the problem here is the integral that goes from 0 to pi halves of 9 times cosine squared theta d theta. So I will remind you that one of the half angle identities, there are a few, this is the one that we're going to use. So open your textbook to the back. Usually there is a list of all of the most relevant trig identities. The one that we need here says that cosine of 2 times theta is equal to 2 cosine squared of theta minus 1. So using this identity, I rewrote it to solve for cosine squared of theta. So cosine squared of theta can be expressed as 1/2 times quantity 1 plus cosine of 2 theta. So if we start just by getting rid of that square, this will become the integral from 0 to pi over 2 of 9 times 1/2 1 plus cosine of 2 times theta d theta. And a little bit of cleaning up here will give, we can just really write this as 9/2 times the integral from 0 to pi over 2 of 1 plus cosine of 2 theta d theta. Right? Again, I don't want you to think too hard about this integral. Again, just a reminder of another u substitution problem that shows up so often that we kind of formalized it for ourselves was, just recall the integral of cosine of kx dx we said was always going to be equal to 1 over k times cosine of kx plus c. And so in this case, we can just use that. So this will be 9 over 2 times. Let's start with 1. The integral of 1 is just going to be theta plus the integral of cosine of 2 theta, according to this little formula that I just shared, is going to be 1 over 2 cosine, sine of 2 times theta. And we're evaluating from 0 to pi over 2. So let's plug in top minus plug in bottom. If I plug in the top, we will have pi over 2 plus 1/2 times sine of 2 times pi over 2 minus, plug in the bottom, 0 plus 1/2 sine of 2 times 0. Well, that's just 0. All right. And again, some of the things that we know are equal to 0. Sine evaluated at 0 is equal to 0. The 2's cancel. Sine evaluated at pi, guess what? That's also 0. So this becomes 9 over 2 times pi over 2 plus 0 minus 0. So my final answer here is just going to be 9 pi over 4. All right, so the next problem, again, I said was similar. It also needs a half angle identity. This time we're going to use the identity cosine of 2 times theta is equal to 1 minus 2 times sine squared of theta. Specifically, if we rewrite this, sine squared of theta is equal to 1/2 times 1 minus cosine of 2 theta. But in my problem, however, I have a sine squared of 2 theta. So we can just double those angles. Sine squared of 2 theta is equal to 1/2 times quantity 1 minus cosine of 4 theta. So I will start this problem by just making that replacement. So this will be the integral from 0 to pi over 4. And this is going to be 1/2 times 1 minus cosine of 4 theta d theta. Again, if you wish, go ahead and factor out that 1/2 coefficient. Kind of makes things a little bit easier. And then we're simply integrating 1 minus cosine of 4 theta d theta. All right, so this will be equal to 1/2 times. All right, the integral of 1 is equal to theta minus the integral of cosine of 4 times theta. Again, just like before, our little shortcut rule was that the integral of cosine of kx dx we said was always going to be equal to 1 over k times sine of kx plus c. And so again, we're just applying our formula here. So this is going to be 1 over 4 times sine of 4 theta. And we are evaluating from 0. And I'm sorry, I just see that I had a small typo. I wrote pi over 2 there. This was supposed to be pi over 4. From 0 to pi over 4. So plug in top minus plug in bottom. If I plug in the top, we have pi over 4 minus 1 over 4 sine of 4 times pi over 4 minus, plug in the bottom, 0 minus 1 over 4 sine of 4 times 0. Again, sine evaluated at 0 is equal to 0. Sine evaluated at pi is equal to 0. So we are left here with 1/2 times pi over 4. So this will be equal to, I get pi over 8. All right, I have one more problem left in this section, and this is kind of like an additional practice, just a practice type problem, but it's a really fun challenge problem actually. We're looking for the integral of 17 times sine squared of x times cosine cubed of x dx. And just like the previous two, this problem is going to rely on a trig identity. This time it's going to rely on one of the triangular identities. So we know that, let's try this again, sine squared x plus cosine squared of x is equal to 1. And so this provides me with the means for replacing, let's say, cosine squared of x is equal to 1 minus sine squared of x. So what I'm going to start by doing here is just rewriting this problem as 17 times the integral of, I'm going to write this as sine squared of x times cosine squared of x times cosine of x dx. And this cosine squared of x right here, I'm going to replace using the identity. So this will be 17 times the integral of sine squared of x times 1 minus sine squared of x times cosine of x dx. All right. So I'm going to distribute, let's see, I'm going to distribute these two terms. This gives me 17 times the integral of sine squared of x minus sine to the power 4 of x times cosine of x dx. And now I'm going to do a u substitution. All right. I'm going to let u be equal to sine of x, which means du is equal to cosine of x dx. All right, kind of makes me happy because that shows up in my problem. So by making the substitution, we have 17 times the integral of u squared minus u to the power 4 times du. And so as you can see, this is now a much more palatable integral. This is equal to 17 times u cubed over 3 minus u to the power 5 over 5. And then finally, let's back substitute. So this will be 17 times, remember u is equal to sine of x. So this will be 1/3 sine cubed of x minus 1/5 sine to the power 5 of x. And then don't forget your plus c on that final answer.